Hi, everybody. My name is Boris Eppel. I'm from the University of Chicago, and it's my pleasure to start the webinar, the O2M webinar series. And before going into the scientific presentation, I would like to ask you to mute your Zooms, so create nice discussion atmosphere. And let me give you a statement. Please, next slide. About the purpose of this webinar. So this webinar is designed to inform everybody about new developments in the field of oxygen imaging and related subjects. And we invite the presenters from academia and industry, and we cover a variety of aspects of oximetry and oxygen imaging and science related to oxygen physiology. And everybody is welcome to sign to these presentations at the website of O2M Technologies. It's oxygenimaging.com, and you will receive announcement of the talks. Before proceeding to the current talk, I would like to introduce the next talks in the series. January 11th of next year, we will have Dr. Esther Latre. She will be presenting the Junior Diabetes Research Foundation. It's an organization which sponsor research in the direction of finding of cure of diabetes, and she will present her novel data and studies in that direction. The next presentation in the series will be at February 8th. And Dr. Bernard Gallet from Louvain Drug Research Institute will be talking about the role which EPR oximetry have in the assessing of the effect of pharmacological manipulation of tissue oxygenation. So let's go back to our today's presentation. It is my pleasure to present Mark Tseytlin, my long-term colleague and friend. Actually, we are talking today from the Brno, where we happen to be together at the trip. Mark will be talking about rapid scan and rapid scan imaging. Rapid scan is a really novel technology, one of the relatively recently developed, although methodology, at least its parts, was known probably for last 70 years, but clever combination of this old techniques and new instrumentation allowed to bring this methodology forward as one of the most efficient methods of acquire electron paramagnetic resonance signals in a variety of systems, large variety of systems. And I think these advantages are making really the revolution in EPR, and I hope to hear it from Mark today. And without further ado, I would like to give the word to Mark. I probably have to mention that, okay, so he's from West Virginia University and have a long distinguished career, and was working in many key positions in key groups in the doing EPR all around the world, including Kazan State University, the Physical Technical University in Kazan, the group of Professor Eaton in Denver University, Dartmouth University group. So Mark, please.
Okay, so today I'll be talking about rapid scan technology and rapid scan EPR imaging, and talk about methodology itself and applications. So my talk will be kind of a big picture introduction to the technology. Okay, but a disclosure first. So my wife and I, we quite recently started our own company, inspired by O2M. So with the same kind of, with the goal to, commercialize our IP, and I hope, that will be very interesting, experience, I believe. So another disclosure, Boris mentioned that actually we both now in Brno visiting Dr. Negenbauer lab. So Peter, thank you very much for hosting us, and I'm actually now sitting. So I didn't share. Oh, sorry, I didn't share it. So again, thanks Peter for hosting us. Remove this stuff. Yeah, there's something weird with it. Okay, this is my outline. So I'll start with like introduction, rapid scan introduction, and briefly kind of describe what rapid scan is and how it relates to other methods, old and new. I'll go over the theory and of rapid scan and how rapid scan signal gets processed, how we get spectra out of EPI signals, talk about applications, some new directions, work in progress, and I'll kind of share some resources which people can use to learn about rapid scan, actually how to play with like a rapid scan software, and it'll be summary. So first, it will be online. I think it makes sense for those who don't, who doesn't know what the EPI is. It makes sense just give brief kind of introduction and definitions. So EPR stands for Electron Paramagnetic Resonance. EPI is very similar to NMR, which is nuclear magnetic resonance. EPI imaging is very much analogous to MRI, which is a imaging modality of NMR. So NMR and MRI, they both observe nuclear spins, while EPR detects electron spins. The physics is, the quantum mechanics, the physics of it is pretty much very similar. So in both cases, magnetic field is needed to observe resonance. And what's important, the magnetic field must have two components, which are orthogonal. And resonance occurs when amplitude of the one component matches the frequency with the other. And the first component is often called B0, and the other, which is changing, it's called B1. So overall, to observe the resonance, you need to change something. In there, like basically three different general approaches. First, you can have a constant B1 and then sweep constant field B0, which is called continuous wave EPR. You may have B0 amplitude constant, and then you can change or sweep B1, and it's the frequency sweep rapid scan or pulsed NMR EPR. And there are some techniques which actually both are changing. I'll briefly talk about it. So most of the people who doing EPR doing CW EPR. That's why I think it makes sense just to go to do the basics and explain what actually CW is, continuous wave. So continuous wave condition for electromagnetic wave is when you have essentially infinite sinusoidal wave with a single frequency, or it's in time domain. On the frequency domain, you have a single frequency, it's like a delta function. And again, in these CW conditions, EPR can be observed if you change magnetic field, and if, again, as I said, there is a certain matching between the external field and the frequency of the excitation. So even for most EPR users, when somebody says CW EPR, what comes to mind is not actually this engineering definition, which is this infinite wave, but something completely different. What comes to mind to most of the EPR users is kind of this experiment when there is a slow changing magnetic field and there is a modulation, and the amplitude of the modulation is selected to be small compared to line widths. So as you modulate, there is this green response. And when you measure the amplitude in the phase of this response, you get the first derivative of the EPR line. And that's pretty much what comes to mind to many EPR users when somebody mentions CW. And I mean, if there's no over, so what's measured is the first harmonic, as I said, and if the amplitude is small, it's called not. So that if there is not over-modulated conditions, then the first modulation harmonics gives you the first derivative. So what I will show you, that's then not the only way CW EPR can be done. And also I show you how CW, it's been evolving and then becomes many different methods. So for example, what happened is actually happened digital revolution. So now we have a kind of better, faster instruments that can capture and process data. With respect to CWP, what happens is now you can over-modulate. So you can increase the modulation of magnetic field. So and if you do so, your response is not sine wave anymore. It kind of becomes couplings, but periodic function. So what this overmodulation does, it generates many multiple harmonics of your modulation. So now if you capture this signal and let's say take Fourier transform, you can extract not just first harmonic as in like a classical CW experiment. You can you can have multiple harmonics, and if you do so, you'll see EPR spectra look quite different from your first derivative one. So like in this picture, when the colors represent different harmonics. So now the question is what to do with them. So we developed algorithms which allow us to take all those harmonics and combine them together to get first derivative EPR spectrum. First, that spectrum will be having better signal to noise ratio, and also in this method you don't worry anymore about overmodulation, because overmodulation kind of broadens your line, which is very damaging for EPR imaging. Let's say if you want to measure oxygen, your line needs to be measured as accurate as possible. So again, here you have better SNR, and also you have you don't worry about distortions because it's all taken into account in the algorithm. So another kind of step forward is CW rapid scan EPR. So rapid scan EPR can be many things, but what I'm developing and I was developing in the Eaton's lab and partially in Dartmouth, it's CW rapid scan EPR. That meaning that like in a standard first derivative experiment, we have CW excitation. It's a sine wave, same thing. But what's different is the shape of the magnetic field, which can be either sinusoidal or it could be triangle, it could be something else. It could be trapezoidal. And what's more important, it's a different way to generate signals, to observe signals, to process data. So for example, if I kind of run this video, you will see that the signal looks quite different. So when you scan magnetic field through the line, if you do it fast, like in a time which is shorter relative to relaxation time, so you see this as magnetization vector in XY plane, how it rotates, and it forms a signal which resembles pretty much an FID. So it's kind of a hybrid between the absorption line and FID. In fact, the faster you go, the more it resembles FID, and if you go slow, it more resembles absorption line. So as you may see, it's a completely different looking signal. Its formation is completely different. Its physics is different. And like later, I talk about what to do with in terms of processing of the data. Okay, to complicate things even further, CW rapid scan is not a single method. It used to be actually the standard Bruker, the old Bruker machines. They had this rapid scan system with 200 Gauss, which was essentially fast first harmonic CW. So now people start calling this fast scan EPR. Also, there is this linear NARS rapid scan method, not adiabatic rapid scan method, developed in the Hyde lab. There is a linear rapid scan. including segmented rapid scan, there is sinusoidal rapid scan. So rapid scans methods are many now. CW rapid scan methods are many now. But also there are non-CW rapid scan methods, like one which are developed here in Brno, when we have frequency scan rapid scan. I mean, it started all in NMR, then in the Ipton lab we demonstrated first EPR, rapid scan with deconvolution procedure, and then now people like he in this lab, they're developing frequency sweep rapid scan. So it's, I mean, it seems like, there is a lot of progress, and EPR spectroscopy becomes, complicated. So that kind of scared you now to kind of explain it better and kind of distinguish between different methods, different approaches. So what I kind of suggesting here is that all CW EPR methods can be distinguished by like kind of 4 factors, right? The first is a magnetic field waveform. The second is the amplitude of magnetic field, changing magnetic fields with respect to the spectral width. The method which is used for detection, and the theoretical model which is used to transform EPR signals into EPR spectrum. So again, definition. So when I say like engineering terms, when I say signal, I mean like voltage as a function of time. And then we say EPR spectrum, it's normally intensity as a function of magnetic field. Another thing to keep in mind that pretty much all EPR methods, they measure actually signals, not spectra. And there is one way or the other to show the spectra. It can be very straightforward, but again, we measure pretty much always voltages, sometimes current, but mostly voltages. Okay, the first thing is a magnetic field waveform. It can be different. It can be, let's say, sinusoidal, as we do now, in my lab at least, most of the time. Or it can be a linear, triangular. So for sinusoidal scan, it's a kind of the best case for engineering. You may have a coil with high inductance. You can resonate this coil and have very strong alternating magnetic field at signal frequency. So it's engineering kind of heaven. But when you have sinusoidal magnetic scan, you have essentially your magnetic field becomes non-linear. So now you need, in terms of mathematics, or in terms of data processing, you need to understand what you're doing and how to take into account that your field is not linear anymore. So the linear field it's opposite. In terms of mathematics, it's much simpler. In terms of data processing, it's simpler, but it's problematic to generate because the nature doesn't have abrupt changes. So here you have kind of discontinuity of the change. That means the derivative, I mean, technically it's not even defined, but it's kind of infinite. And nature just doesn't do it, right? So you have some kind of smoothing at the end. So to get a perfect linear scan, it's challenging, especially if you want it to be fast and to be at white. So in terms of scan amplitude, so the classical approach for first harmonic, as I mentioned, you want your amplitude of modulation to be smaller than line width. So this is the EPR spectrum with line width. You may have it a little bit broader, then you have multiple harmonics, which you can, again, reconstruct it to a signal spectrum. Another approach is when you have your sweep of your magnetic field exceeds your line width, and that's how classical rapid scan is done. So in one scan, you actually capture the entire spectrum, while here you go like essentially segment by segment as you move along the spectral dimension. In terms of methods, again, the old approach is analog demodulation. So using, for example, lock-in amplifier, and then you digitize your signal at very low frequency. And that way you can measure single harmonic CW EPR spectrum. Another approach is that you direct your signal and you do digital demodulation, as I just showed. Like that would be the case of multi-harmonic CW EPR, when you can capture your signal and then in computer you can do Fourier transform, you can extract harmonics. So that will be convenient to do using something like real-time FPGA, for example. And the next approach is direct detection. When you digitize EPR signal as is and you use it as is. So that used to be pulsed EPR when we detect kind of relatively short FIDs or echoes, but now that's the case for rapid scan. We need to detect an average in real time rapid scan signals without losing any, ideally not losing any data points. And for that, you need to fast digitizers. So now it's kind of becomes a little more interesting, like theoretical model. So two kind of models can be distinguished, which can be called, the first model will be called slow scan. It's a memories model. So essentially it's the model of a slow scan. If you slowly move your resonance frequency or field through EPR line, essentially in a given moment of time, your signal will be essentially proportional to the intensity of EPR line. And that's how CW, like a classical CW EPR works. And data processing essentially is extremely straightforward. You essentially have a time domain signal which you just simply map in the field domain, and that's how it works. Even if it's a derivative, it's pretty much the same approach. So again, that's how first harmonic standard CW works, multi-harmonic, NARS, and you may have actually slow scan rapid scan API situation as well. So, but now if you do this experiment I showed you before, when you go through resonance in time which is short relative to the relaxation times, obviously this model of slow scan doesn't apply. You cannot just map your time domain signal to the frequency domain, because now you have kind of a history, you have a memory. So the signal which you observe, let's say 100 nanoseconds or microsecond later, it actually was generated in the past. So this the approach of remapping time domain to field domain, that just doesn't apply. And here there is a need for a new approach, and that approach would be a linear time invariant system approach, where the spin system is approximated as a linear time invariant system. So a little bit about this system. So what is it? This modeling is, you can find it pretty much in many branches of natural sciences, engineering, spectroscopy, astronomy, when a system is approximated as a linear. For example, filters, even in everyday life, if you have a small perturbation, the chances that your system is linear are quite high. For example, if you go to a store, buy a can of beer for $1, and then you want to buy, 2 cans of beer, that will be $2, 3 will be $3, so it's linear, right? If you come to next day, if there is no inflation, and the chances are the next day you'll buy this can of beer for the same $1. But now you come to the same store with $1 million. What are the chances you buy 1 million cans of beer? They're pretty much low. So this approach is any system with a small perturbation, it can be, approximated as linear. The question is, where is the threshold? So when it comes to EPI, it's kind of pretty much obvious that first that any linear system is uniquely described by its impulse response function. Essentially, if you have a system and you apply a very short impulse, then output would be this impulse response function. And it's kind of obvious for EPR that will be FID. So if you apply extremely short pulse, the output will be FID. But then you have arbitrary input x of t in this slide. So then the output would be a convolution of your input and your FID. And this this is pretty much mathematics of a linear system. So if you input increases by a factor of r, the output is increasing by a factor of a. If you shift in time by tau, the input output shifts by tau. But what's really important for us is that the convolution in the time domain becomes multiplication in the frequency domain. That's the key equation used for rapid scan data processing. Okay, so closer to EPR, to magnetic resonance. So if the spin system is approximate as a linear system, then then as I just described, what you measure in the experiment will be convolution of your excitation function and FID. And then, based on that theory, we know that Fourier transform of ID is a spectrum. So if we take Fourier transform and divide Fourier transform of the signal over the Fourier transform of B1 function of t, we immediately get spectrum. Kind of problem solved in a sense. Except there are some caveat, there's some features, some details. For example, you don't want to divide by 0. So you need to be careful how you select this B1 of t function, so that in the frequency domain it approximates as 1, so you don't have ill-post problem. So you have a stable solution. So now if you apply this theory, if you have low power excitation, apply to a spin system, you measure output, you take Fourier transform, you divide frequency domain, you have your spectrum right away. And there are methods actually that do exactly like that in NMR and in EPR. So the limitation will be, again, the spin system must be well approximated as linear. And you need to actually excite the whole spectrum, because you don't want to truncate FID. And that's why in rapid scan we need a complete scan of the spectrum. And also it becomes immediately clear that in a rapid scan experiments, when the people use frequency sweep, then this theory immediately applies. So you just immediately use it as is immediately. So you don't need anything else. So it's just essentially one line of code to get your spectrum. But it's not so for CW rapid scan, because your B1 is a constant. If you take Fourier transform of the constant, you get nothing useful. And I explain a little bit later how we go about solving this problem. So again, if you have frequency sweep rapid scanner called FS, already using that linear approach, you can already get your spectrum. But at that point, I want to make a statement and explain it later. So I want to make a statement saying that in linear regime, CW EPR is equivalent mathematically to the frequency sweep EPR. So if you change your field at constant frequency, or you change your frequency at constant field, at the end, these two situations, they mathematically equivalent. So in the beginning, I kind of touch upon these definitions, right? The experiment number 1, when B1 is constant, B0 is changing. Experiment number 2, B0 is constant, B1 is changing, right? So what I'm saying that in linear regime they're equivalent. It kind of obvious if you do slow scan, right? If you do slow scan, you slowly change frequency, or you slowly change magnetic field. You give if it's a Lorentzian line, you give line. So it's kind of obvious. But what's important for us is that this is actually also true for transient rapid scan signals. And another thing what's important, that there is a transformation which transforms experiment number 1 into experiment number 2, and there is an inverse transformation which does the opposite. So we need to figure out what this transformation is, and then then actually, if we do so, we can apply the theory, this linear system theory, and get the convolution and get our spectra in rapid scan, CW rapid scan experiment. So essentially, it will take two steps. First, we're transforming experiment number 2 and experiment number 1, and then we do the convolution, and that's it. It's very, very straightforward. But I mean, what how to do, what kind of transformation it is. In fact, it's also very, very simple. Essentially, what it comes to is a change of a reference frame. So in magnetic resonance, we will know in terms of like changing reference frame when it comes especially of like a single frequency excitation rotation frame. If I apply the same logic to rapid scan, when magnetic field is changing, so then we kind of as we change magnetic field, our alarm frequency also changes. So if we kind of jump on a reference frame associated with the changing alarm frequency, then exactly that's exactly what we get. We get a situation where we have the signal becomes a frequency sweep signal at a constant magnetic field. So, and the transformation is just essentially it's a multiplication. Okay, and then as you do so, you just apply this deconvolution and get your spectrum. It seems that essentially it's like 2 lines of code, but I mean, in practice, there are a lot more programming because there's some problems, some details again. But before I go to details, I just want to kind of tell you why do we care? Why would we care about all this at all? Right? And the short answer is, so rapid scan gives us increase in sensitivity, and also it permits fast imaging because you can capture your EPR spectrum over, I don't know, millisecond or less. So for example, in my lab, we do, like we measure, let's say 2600 spectra over in 3 minutes. And it's only mostly limited by SNR. We can capture all 2600 spectra probably in just several seconds, which would be quite impossible with a standard CW approach. And sensitivity. So what's underlying physics in terms of sensitivity? It's very straightforward. Linear regime. In linear regime, as I mentioned, the higher the input, the higher the output. So if you increase your B1, you increase your signal, right? And because the system is linear, you increase input, you increase output. So the only thing that what's needed is that the system so the spin system remains linear as you increase your excitation power, and that's what rapid scan does. As you go fast, the faster you go through a line, the kind of you can shift the threshold of the system being linear at higher and higher power. So that's one thing. Another thing is that in rapid scan we measure absorption, which overall signal could be like factor of 3 stronger than its derivative when it's measuring in field modulated way. In terms of practical application, so CW may be saturated at certain power, but rapid scan can unsaturate the signal, so you can go again to high power, so you have a stronger signal. So for that reason, from practical standpoint, samples with long relaxation times, especially T1, they will be beneficial for rapid scan. And as I mentioned, imaging, because in EPR imaging, you can capture multiple lines, have multi-line imaging spectra, while in pulse, you're pretty much limited just only single line. So there's some challenges. You need to generate wide, fast magnetic scans. You need to be careful that your bandwidth doesn't exceed the bandwidth of the resonator. There's a microphonic effect, which I briefly talked about shortly. And another important thing is, as you increase power, you get a stronger signal, but this is still CW. That means there's a possibility of having high reflection. So all tuning and coupling needs to be done, I mean, much better than in the standard CW case. And also there's a limitation, you know, in terms of averaging. You need to capture the complete FID. So you're limited by T2 star time in terms of signal averaging. So briefly, I mean, there are several problems, but one of the most important, one of the key problems with rapid scan is that it's called so-called background problem. So essentially, if you have a magnetic, if you have a modulation coil in a electromagnetic field, you have a speaker. So they vibrate, they create mostly first harmonic microphonics and a little bit of a second, depending on what forces are acting on them. So same problem exists in a standard first derivative CW, but this microphonic signal becomes just TC line, which is subtracted by just offset. But in rapid scan, we see it as is, and we need to deal with it. Because in this background signal, it's fundamental harmonic, and you cannot distinguish it from EPR. So I just want to briefly show you how using spin physics we're solving the problem of background. It's kind of very neat approach. So in rapid scan, as we go through line, remember we're changing magnetic field. So as we go through resonance, we have resonance in which it's a magnetic field gets increased. So as magnetic fields gets high and high and high, you have more frequency increase. So your frequency of Warm frequency increases until your signal disappears. And when you go down field, then actually frequency decreases. So now if you take Fourier transform of your signal, the signal which like up signal appears on one end in the Fourier in the frequency domain, but this signal appears in the opposite end in the frequency domain. So your up scan and down scan, you know, rapid scan signals, they completely decoupled in the frequency domain, thanks to, you know, this spin physics. And we published some papers with, I mean, describing how to use this approach. We kind of separate up and down. We find the background, we subtract it, and this method works very well. So I can running a little bit out of time. I'm just go briefly over some of the major applications of this technique, and most of them will be imaging. So in my lab, we have two systems. This one is one rapid scan system. We use to measure, you know, mice, for example. And we kind of completing the other system, which is a collaboration with my colleague. It's a PET EPR imaging. It works now as a rapid scan imaging system, but we need yet to add, you know, the PET inside this magnet. But pretty much we have two rapid scan systems which we built in the lab. So in terms of what you can do, let's say in Vivo oxygen mapping in a mouse. So another example in collaboration with our colleague Benoit Trescart, we did this. I mean, mostly him. We just imaged for him. We demonstrated that we can do imaging of enzymatic activity. He made a sample. His lab made a sample when there is a substrate product and one gradually becoming the other. So it was I think one of the first example when we demonstrated EPR imaging of enzymatic activity. Another example, we demonstrated real-time rapid scan EPR co-imaging in 2018 when we put together a phantom with PET tracer and EPR, I believe it was Tritil, and we demonstrated we can do co-imaging in real time. And this is but it was very kind of we just put together a system with very small resonator. But now we're assembling a system which allows us to measure mice. This is our gradient coil, which goes in this magnet, and the PET system goes into that aluminum frame. And there's rapid scan coils underneath this gradient coils. So another thing, when I was at Dartmouth, we tried to do rapid scan imaging like clinical system. That's me in the magnet. And you can see here there is a EPS rapid scan EPS spectrum. So we modified the existing system. It was not fully optimized for rapid scan, but we got some results. We actually in West Virginia University, our university bought the clinical system. So probably we'll continue working on that project and build a rapid scan clinical system. So another application is so in our lab, so we're building pretty much everything from scratch, and we have like several different types of 3D printers. And there's this the printer which prints with resin, and what we realized that for that printer to work, it needs to remove oxygen. So when you shine UV light in that resin, when it prints, the first step is to photoinitiator interacts with oxygen and it removes oxygen, because oxygen is an inhibitor of photopolymerization. And after oxygen is removed, only then the polymerization starts. And we figured that would be an interesting project for EPI imaging, because oxygen plays a critical role in the 3D printing. So we bought an inexpensive Chinese printer for like $200, and we replace extruder by a syringe. We had resin with EPR crystals in it, oxygen sensitive crystal. We even tried to print spiral and image oxygen in it. Then we put this resin with crystals in a bottle when we kind of shine light on it, and we observe how polymerization front propagates with polymerization. I mean, we observe actually it's imaging of oxygen. So we can observe as polymerization proceeds, as oxygen gets depleted. And in one of the samples, there is a procedure of curing. When you 3D print something, it's not complete. You put it in a chamber, which is irradiated UV to kind of cure the residual. So in this example, we demonstrated that actually after curing, indeed, the oxygen gets depleted, residual oxygen gets depleted in 3D prints. And we published this paper after a lot of backs and forth with editor, because for them EPI it's something strange. Another application is for rapid scan is actually measuring magnetic field. So the way we do 4-dimensional imaging is it's a spectral spatial imaging. Essentially, in each voxel of our samples, we measure spectrum. So now we have, as in this case, we have a small speck of, I think it was some magnetic nanoparticle in resin. I think it was fraction of millimeter in size. So we put it in a PR solution, and this small particle creates magnetic field around it, which is kind of obvious. What it does, it kind of in each voxel it shifts EPR line a little bit. And now if you do 4D rapid scan imaging, you actually can image a magnetic field created around that small thing. There are multiple applications. We see them. At first, there is a need to image a magnetic field in some kind of small object, especially, let's say you can get inside with the probe. I can put tritium inside and do image and see really how magnetic field is distributed inside. You can do it for shimming, for example. And what's also interesting with rapid scan, you can not only see image DC magnetic field, you actually can image slow AC magnetic field. Again, I think there are potential applications for that technology. So, and then I'll kind of want to switch to some work in progress and kind of future direction. So that, as I mentioned, when you do rapid scan in spectroscopy imaging, you ideally need to go to higher powers. And as you go to higher powers, it becomes more and more difficult to tune your system because you have more reflection. So, this problem needs to be solved, especially if you have in vivo situation. If a mouse which breathes, breathing mouse modulates, your coupling and tuning quite a bit. So this is kind of work in progress. Hopefully we, so this is a project of my PhD students. Hopefully we'll publish the paper describing all the details. But the idea is to use kind of discrete digital tuning and coupling instead of the standard approach, which it's if you have AFC in the Bruker system, it's like a mouse and cat. So you always try to catch the frequency as it changes, as the sample changes. First, there are two problems with this approach. First, you can lose your mouse if the changes is quite a bit. And another thing for imaging, if you do AFC, your frequency may change. And for rapid scan, especially if it comes to imaging of narrow lines for oxygen, for oximetry, if your line starts moving, I mean, you're screwed. You're getting, broadening of your line. You're losing all important information. So instead, with rapid scan, we select a different approach, which you have very fast scan of frequency. You find your resonance, your coupling and tuning, and in a very short time you have both. So currently we got somewhere around 80 milliseconds for complete tuning and coupling of our system, fully automated. I'll go to reduce it to somewhat of 10 milliseconds so that you can really do it with mice, breathing mice. Another approach is this is what they call high risk, high impact. So recently we got an RR21 to do EPR imaging without using RF excitation at all. So the idea here is to use rapidly rotating magnetic field to create non-equilibrium situation and measure rapid scan kind of signals without using any powers at all. I mean, it's still a changing project, but I hope maybe in 1.5 years we have some result. But if it works, that will be really great because it solves many problems with saturation, with heating your sample, etc. So another project is it kind of is becoming obvious that rapid scan imaging will be a great tool for bioprinting, because especially for thick objects, because you really want to know if oxygen and other nutrients are delivered in your bioprint. You want to know what pH is, and for that rapid scan will be a great tool. So again, we have this inexpensive 3D printer. We modified, we make a bioprinter, which kind of prints. It's called fresh technique. So far we can print what we call the model of vasculature. It's kind of empty tube printed, in this case alginate. Also we developed a technology to print with GELMA. And I go here again, so we completely happy with our auto tuning system. Our goal is to start doing 5D imaging, which is like 3D X, Y, and Z, spectral and temporal, because when it comes to all this bioprinting stuff, you don't want only measure oxygen, but you also see how much oxygen is delivered, how much oxygen is consumed. You want to see kinetics. So this is a long-term project, but I think rapid scan EPR image is a great tool for it. Another thing is that actually we started with Boris quite a long time ago. Here is the idea to combine rapid scan and field modulation. So on the left, there is an example when you can reduce, decouple. If you use a bimodal resonator, you can use rapid magnetic field scan to excite spins at one frequency and detect echo on the other frequency. So by doing so, you can completely, kind of decouple quite strongly excitation from detection. And you have all kind of very interesting physics here that just don't have time to, go about it. Another application is if you apply modulation to your extended spin echo, what happens in between the pulses, you change the alarm frequency, and when doing so, actually changes phases. So by selection of this modulation, you can control the phase of your echo. And that means actually you can do kind of rapid scan phase cycling, which is another cool thing you can do with rapid scan. So almost done. I just want to go over EPR resources. This is our recent publications, what recent algorithms. This is the most recent thing when I published a kind of general solution for rapid scan API deconvolution, when you can pretty much use any arbitrary waveform to get your spectrum. And there is also a review recently published of rapid scan, continuous wave rapid scan API review. So 2 years ago, I was here in Brno mostly at the same time, also with Boris, by the way. It was this EPR school, and I made some interactive software using MATLAB, and I downloaded on my lab website. It's still there. So if you're interested in downloading and playing with some of it, you're welcome. And if you have any questions to use, if there's some glitches, let me know. I'll help you. On the same website, there is a software how to go about solving bulk equations for rapid scan. If you do so, you may see these rapid scan signals and MZ changes with T1 time. Also, you can use EasySpin to find steady state solution of bulk equations. That's much faster and more accurate. Also, there is our version of this on our lab website. This is a GUI of that program I just mentioned. You can download again from our website when you run some simulations, change parameter, and play with it. So this software includes this frame transformation, step 1 I talked about, also for your deconvolution. So you're welcome to play with this software again. If there are glitches, let me know, or you need update. I mean, it's been 2 years, but I mean, it worked 2 years ago. There are some suggested exercises you can do with that software. So summary. Essentially, CW rapid scan as of today is essentially a sensitive and enhanced version of the standard CW. In some cases, we got in the ETAS lab, we did some measurements. We got up to 2 orders of magnitude sensitivity enhancement for narrow lines. You have a narrow band excitation, CW excitation, but you have broadband detection as in pulse. Again, most of the SNR gain comes from using high power and faster scans. So what's important that the system remains linear even at high powers. There's no dead time compared to pulse, but you need to be careful that your high power saturation may saturate your LNA. But again, for that purpose, you need really good automated tuning and matching approach or method. There's some limitation to the how you can do your scans. I mean, pretty much most of it is described in that review chapter. So you can, if you're interested, you can go over it. And it's kind of probably the last slide with kind of personal opinion. The things are going now. So first, I showed you it's like kind of good news, bad news. The good news, I showed you that the best spectroscopy imaging, it's been evolving. And the kind of sad news is that there are so many great methods, but they're not readily available to users due to many reasons, more expensive. Also, there is a slow adaptation of this new technologies. In that case, the companies like O2M, they doing very great. They're trying to address the need and for reliable, affordable, easy to use, state-of-the-art EPA instruments. It's really great. So another great news for us, my background actually in physics, so I learned all the engineering as I went. So for guys like me with mostly physics background, but without, I have kind of acquired engineering background. Now they're really great times because if you have an idea, you have so many great tools, instruments which can assemble in a leg of fashion to make your idea come true. So now it's really great times for status quo disruption. And another good news is, as you see, there are more good news than there are bad news. So now I want to end with thanking people who I worked with. So people in my lab, people in our EMR center. There's a link here. collaborators, and funding. And with that, thank you very much. So I can take questions.
Thank you, Mark, for this wonderful presentation. I think we are open for the discussion. And let me ask you probably the first question in this discussion. So you went with the examples over the things which RapidScan does the best over the present continuous wave methodology. Can you tell what RapidScan can do which continuous wave cannot do at all?
Okay, so the way the things are now, it's pretty much the same. But there is a great potential. For example, in terms of like saturation, in continuous like the standard CW approach, your T1 and T2 relaxation times, they kind of come together, like T1 times T2 times P1 squared. So in RapidScan, you decouple T1 from T2. So there is actually great potential, for example, to measure T1s in RapidScan. I mean, this is kind of, we discussed that when I was even in the group, but I mean, but there are ways to, for example, measure T1s. And that would be great for measuring oxygen, for example, because I mean, your group demonstrated that T1 is better way to do oximetry than T2. And another thing is sensitivity. Another thing is, again, imaging. I mean, if you're using standard CW, I mean, there is no way you can do 4D or 5D imaging. It will take forever, and people know that. But with RapidScan, you can do it in, I mean, in seconds if you have extremely strong, you know, signal. That's the major thing, I think.
Thank you, Mark. Please come up with other questions.
It's a comment from Igor on the chat. Hi, Igor. Thanks for joining.
You are welcome, and thanks to Mark for a nice talk and reminder about RapidScan. Indeed, and nice to see Mark and Boris. We are from the same university, Kazan State. I just would like to mention something which Mark maybe not so much stressed, that RapidScan EPR is not stationary EPR. And in principle, continuous wave EPR, how it's called on this side, is on the Russian side called stationary. Stationary means that your spin system is on Boltzmann equilibrium. Actually, you pump with a microwave and reach stationary condition where the spin polarization is low. It's not a case for RapidScan, and this is one of advantage that you pass quickly through resonance. You are not on a Boltzmann, and you can use much more power as a consequence, higher B1 and higher your signal. That's why any, let's say, saturated samples, when you need 20 to 40 or even 60 decibel attenuation of your microwave source, could be measured at about 20 to 30 or 60 decibel higher power. On the same factor you will get in a signal, and this is one of another major advantage of RapidScan, what Mark not exactly mentioned.
Okay.
Right?
Kind of.
So
Yes.
20 dB, I've seen myself. You do, for example, E prime in a quartz.
No, I mentioned that we observe up to 2 orders of magnitude enhancement. Which
yes, 2 orders of magnitude, simply because of that. To. Yeah, thank you.
Mark, I have a question. So you mentioned that you use high power for RapidScan. Does it mean when you do in vivo imaging, you heat up the mice?
Yes, to a more extent, yes.
Another question was, wanted to know a little bit more detail about your R21.
Yeah,
what's the idea
behind it? It's actually now it's in the stage of patent disclosure.
Okay.
But I can big picture.
Okay.
I'm not supposed to just talk in details about, because I will submit a patent with W. But this is very challenging project. If it works, that would be great. And we'll see.
Okay, good luck. We'll keep in tune to see. Are there any other questions? Looks like not. So, are there?
We go to the final words.
Yes. If there are no questions, thank you all for joining, and I hope you will tune up again in January when we will have Esther Letris. She's a Director of Cell Therapy in JDRF, Juvenile Diabetes Research Foundation, and she'll talk about JDRF and why oxygen is important for islet encapsulation therapies. Thank you. Bye.
Thank you.
Thanks, Mark.